Math 2414, Trigonometric Integrals, Integrating a Product of Sines and/or Cosines, Part 2. This is a direct continuation from Part 1, so if you didn't watch Part 1, you might want to go back and watch it. I will quickly summarize where we kind of left off, because we didn't actually finish the integral. Don't worry, we're going to. Well, we were integrating sine cubed x cosine squared x dx, and we eventually decided to let u equal cosine x and du equal negative sine x dx. In an effort to create the du package, we needed the dx, which was present the whole time. We needed a sine x, which we had 3 of, so we borrowed one of them to put with the dx and left the other 2 behind. But we also needed a negative, and a negative is always easy to balance. Just throw it in where you need it and balance it with the negative on the outside. So everything double underlined over there will become du. But the problem we ran into was our choice of substitution was u equal cosine x, which meant that the cosine squared is going to become u squared. However, we still had a sine squared left over. We had 3, we borrowed one of the sines to create the du package. But what do we do with the other sines? Well, because it's sine squared, we could change it to 1 minus cosine squared. And again, changing sine squared to 1 minus cosine squared is just using a Pythagorean identity. And the advantage to that, by changing sine squared to 1 minus cosine squared, in addition to having the du and the u squared, now, because this is in terms of cosine, which we're calling u, 1 minus cosine squared x becomes 1 minus u squared, which means that our integral is now, don't forget the negative, integral of 1 minus u squared du. Why don't we go ahead and polish off this integral, and then we'll go back and review what drove the decision to let u equal cosine and turn it into a technique. We'll leave the negative out in front just for now. Let's go ahead and distribute the u squared, because we integrate addition and subtraction problems. We really don't integrate products. So distribute to destroy the product and get u squared minus u to the 4th du. And now just integrate term by term, and we get negative 1/3 u cubed minus 1/5 u to the 5th plus a constant of integration. And now we can change the u back to cosine. And while I'm at it, I'll go ahead and distribute the negative and put the positive term first. So again, I'm going to distribute, that'll make this positive, I'm going to write it first, 1/5. U is holding the place of cosine, so this is 1/5 cosine to the 5th power x. And then minus 1/3, u is representing cosine, so cosine cubed x plus c. I claim that's the antiderivative. You could take the derivative, the fractions would disappear, factor out a cosine squared, and you should be able to turn the rest of it into sine cubed. Something sounds funny there. I'm not going to bother checking the derivative, but of course in my mind I'm like, yeah, you are. Something seems off here. Oh, chain rule. I've got chain rules. Okay, so if you check the derivative, do the chain rule, factor out a cosine squared, and maybe do a Pythagorean identity, you should be able to restore the derivative of this answer back to this challenge. You should accept that challenge. But I want to really focus on the moral of the story, which was what drove the substitution. Why in this problem should we let u equal cosine instead of letting u equal sine, which in the previous video we saw crashed and burned. And the answer was because of who had an odd power. Think about why pulling a sine off worked here. We had 3 sines and we borrowed one for the du, which kind of forced us to let u equal cosine so that sine could be used as part of its du package. But the reason that worked is because the power of the sine was odd. Stealing one of the sines for the du package left it even, and being an even power, specifically 2, allowed us to use the Pythagorean identity to rewrite it in terms of cosine. In other words, rewrite it in terms of our substitution. So without further ado, let's begin formalizing the technique here. And we're going to call this how to integrate the integral of sine to some power. Let's call this power, I guess p is a good letter for power. Sine to the p power of x times cosine, and I need another letter for power. Can't use P again, I guess we'll use the next letter, Q. Dx. All right, so how to integrate the integral of a power of sine times a power of cosine dx. And this is going to be built over the next few videos, but let's go ahead and start with this one. If one of the powers is odd, okay, so in this case sine cubed was odd, let u equal the other trig function. Now I'll elaborate on this in a moment, but let me kind of explain what I mean here. When you're integrating a product of sines and cosines, if one of the powers is odd, which was this one, here's the odd power, you let u equal the other trig function. And again, the reason this works is if you take the derivative of the other trig function, like the derivative of cosine, you will need a sine for its du package. So you'll have to borrow one of these from the odd power, which knocks it down to an even. And being an even power, you can now use a Pythagorean identity to change it back in terms of the other trig function. But this is the catalyst. I could write a more detailed sequence of steps, but this is the catalyst. If you're integrating a product of sines and cosines and one of the powers is odd, you let u equal the other trig function. Let's take a look at one more example and then we'll elaborate on this, plus answer the question, what happens if none of the powers are odd? Well, if none of the powers are odd, what would that make them? Assuming that they're integers or whole numbers, that would make them even. So what happens if they're both even? Well, we're not there yet. So let's take a look at another example. Let's integrate, let's do sine to the 4th power of x, cosine to the 5th power of x, dx. According to this strategy, what should I let u equal? By the way, as usual, you're always invited to pause the video and try to beat me to the answer, and then resume the video and see if we get to the same place. According to the strategy, if one of the powers is odd, you let u equal the other trig function. One of the powers is odd, cosine, so we're going to let u equal the other trig function. Not the other trig function with its power, just the other trig function. So we're going to let u equal sine of x. Then du equals cosine of x dx. So we don't need any extra negatives. Let's see what happens. We're going to need to borrow a cosine for the du package. So let's start by setting up the du package. There's my sine to the 4th, there's my cosine to the 4th. And I'm stealing one of the cosines, so it's over here. And by stealing one of the cosines, I've created both pieces necessary for the du package. So all this will become du. Now u is equal to sine, which means that sine to the 4th is going to become u to the 4th. But what do we do with cosine to the 4th? I think I need to add a little bit more to this. If one of the powers is odd, let u equal the other trig function. When the time is right, use a Pythagorean identity, ID for short, to replace unwanted trig functions. Now you may be saying they're all unwanted, but what I mean by unwanted trig functions is by setting this off and saying u equals sine of x, I have 4 cosines left over that I don't want. Now, how do I know this is going to be able to work? Easy. This guy used to have an odd power. That's why I wanted to borrow one of his to make it even. Borrow one of his to make the du package for this substitution. And being an even power, every even power can be written as a power of a square. In other words, cosine to the 4th power of x is equal to cosine squared of x squared. And as long as the power is even, you can always write it as the power of cosine squared. Well, cosine squared is 1 minus sine squared of x. But that has a square on the outside. And because sine is equal to u, this is going to become 1 minus u squared squared. So you do have to do a little bit of finagling, if you will, a little bit of smoke and mirrors, in order to get the unwanted trig function out of there. I don't want cosines. I already used the one I needed. I want sines. Cosine now has an even power. Thank you for letting me borrow one of your cosines. And as an even power, I can always write it as a power of cosine squared. The cosine squared becomes 1 minus sine squared, and then I make my substitution of sine. Excuse me. Try to finish that sentence without taking a drink. Anyway, if we jump through all these hoops, then the cosine to the fourth x will become 1 minus u squared squared, thanks to the power of cosine now being even. All right, let's see what happens now. Everything here is really kind of a side thought, so maybe I should put a cloud around it. I would write it down. I mean, it's not impossible to see through that, but trust me, especially as a student, you want to write that down. So where's our integral now? Sine to the fourth x becomes u to the fourth. Cosine to the fourth x, thanks to this Pythagorean identity, now becomes 1 minus u squared squared. And then the cosine x dx becomes du. Now we're not out of the woods yet. But all we've done is transform it from a trig integral to an algebra integral, and more specifically, a polynomial. It's factored, we're going to have to bust it open, but at least I know how I can see the path to the end now. Let me check the time on this. I know this video has been going quite a while. I will wrap up this problem, and then we'll do another example. I've got at least 2 more for sines and cosines. All right, so let's just review what happened real quick. Integrating a product of sines and cosines, one of them was odd. So I let u equal the substitution of the other trig function. In this case, u is equal to sine of x, because cosine had an odd power. By that choice, du is equal to cosine of x dx, so I had to borrow one of the cosines to make the du package. The sines all became u's, but the cosines, now having an even power, could undergo this transformation, thanks to its power being even. And by changing it from cosines to sines, I could take advantage of my substitution one more time. And now I've got it completely down to a u integral. I was trying to think if there was a clever way to do this one, but now's not the time for cutesy and clever. Now's the time to just bust this open. If you were to write the 1 minus u squared twice, because the 1 minus u squared is being squared, so 1 minus u squared times 1 minus u squared, and then FOIL it all out, multiply it all out, you would get 1 minus 2u squared plus u to the fourth du. But again, we don't integrate products, we integrate addition and subtraction problems. So let's get rid of the product by multiplying, distribute the u to the fourth, and I'm going to put it from highest power to lowest power. U to the fourth times u to the fourth is u to the eighth. This is the time to add powers. U to the fourth times negative 2u squared is negative 2u to the sixth. U to the fourth times positive 1 is positive u to the fourth. The product is gone, and now I can integrate this guy, and not only am I going to integrate it, I'm going to unsubstitute at the same time. So before I write the u, I'm going to replace it with sine of x. Integral of u to the eighth is 1/9 u to the ninth, but u is sine of x. So 1/9 sine to the ninth power of x. The integral of 2u to the sixth is 2/7 u to the seventh. So 2/7, but instead of u, I'm going to write sine. 2/7 sine to the seventh x plus the integral of u to the fourth is 1/5 u to the fifth, but the u becomes sine of x, and we get 1/5 sine to the fifth x plus c. I challenge you to take the derivative and see if you can restore it back to that. Should work. A little trick here because of the algebra involved. All right, so again, to integrate a product of sines and cosines with powers, if one of the powers is odd, you let u equal the other trig function. When the time is right, and by the way, the time is right after you've borrowed one of the odd-powered trig functions to create the du package. When the time is right, use a Pythagorean identity to change the unwanted trig functions into whatever the substitution is asking for. In this case, changing these 4 cosines into some sines. And then you can finish the substitution, and then you may have to do a little bit more algebra before you do the integration. In fact, the biggest problem here is not the calculus. It's the algebra and the trigonometry. Go figure. We're going to take a look at another example because this says what to do if one of the powers is odd. But what if they're both odd? What if both powers of sine and cosine happen to be odd? Let's see.